Right. Well, welcome everybody to today's webinar on streamlining access to RCSB PDB APIs with Python. As we're waiting for more people to sign on, I just wanted to first start with some quick housekeeping slides. So for any questions that you have during today's webinar, please ask them using the Q&A feature provided on Zoom. My colleague Joan Seguro will be monitoring it and will try to address questions as they appear. For any questions that remain unanswered by the end of the webinar, we'll try to address them at that point. Just to emphasize, today's webinar will primarily be focused on the sequence coordinates API and models APIs at rcsb.org and their usage via the RCSB API Python package. So if you're new to our APIs or the RCSB API Python package, I encourage you to please check out our past webinars for more in-depth overview and introduction to those. And links to them are provided here. So a nice introduction to our APIs in general is provided at this link at our PD 101 training events page. And for our Python package, there is a nice introduction to that with a specific focus on our search and data APIs. And that can be found at this link here. All right. Well, with that, I think we can get started. So again, and welcome to today's webinar. And I'm Dennis Peel. I'm a scientific software developer at the RCSB Protein Data Bank based at Rutgers University. And today we'll be talking about streamlining access to RCSB PDB APIs with Python, with a specific focus on our sequence coordinates API and model server APIs. First, just to give you an idea of what to expect in terms of timing for today's webinar, I'll begin with about a 10-minute introduction to the PDB rcsb.org APIs, as well as the RCSB API Python package. I'll then move into an overview of what the sequence coordinates API and model server APIs are capable of and what kind of applications that can be used for. And then I'll switch gears into a live demonstration in which I'll work through some Jupyter notebooks on demonstrating the usage of the Python toolkit. And these will be accessible via Google Colab. And we have 3 different notebooks prepared for you. I have one for a sequence coordinates API walkthrough, one focused on our model server API, as well as one that touches on some more advanced use cases of our search and data API. I'll then conclude with some announcements and open the floor for Q&A. All right, so with that, we can dive in. So the Protein Data Bank was first established in 1971 as the first open access digital data resource in biology, containing just 7 crystallographic structures of proteins. It has since grown to house more than 253,000 experimentally determined 3D structures of biological macromolecules, owing thanks to the tens of thousands of structural biologists around the world who submit their structures for deposition to the PDB archive. The PDB archive is jointly managed by the Worldwide Protein Data Bank, or WWPDB, which consists of the RCSB PDB in the US, where I'm based, the PDB-E in Europe, PDB-J in Japan, PDB-C in China, as well as 2 specialist repositories, the BMRB and EMDB. We are committed to ensuring that PDB data remains fair, that is findable, accessible, interoperable, and reusable. And one key way that we strive to achieve this is by distributing PDB data under the Creative Commons CC0 license, which means that anybody around the world can access these data and use them with no limitations on usage. The RCSB PDB web portal at rcsb.org provides a one-stop shop for 3D biostructure data by delivering access to the more than 250,000 experimental structures from the PDB archive, alongside more than 1 million computed structure models, or CSMs, from AlphaFold DB and Model Archive. In addition to these structural data, we also offer a rich collection of tools and features that you can use to search, analyze, visualize, and download these structural data. And on a weekly basis, we furnish this collection of structures with annotations from approximately 50 external resources, such as Uniprot, SCOP, CATH, and more, which add evolutionary and biological context to the structural data. Importantly, all these tools and data are made accessible via a powerful set of application programming interfaces, or APIs. The 2 main APIs underlying rcsb.org are the Search API and Data API. The Search API powers all search capabilities, which allows users to perform complex multimodal queries on PDB and CSM data to retrieve a set of matching identifiers. The Data API powers all data retrieval tasks, So it lets you fetch tailored subsets of data, such as metadata and annotations, for a given list of PDB or CSM IDs. So for example, the search API can be used to search for structures, and you can do this using any of our advanced search options, which includes full text search, attribute search, sequence similarity, structure similarity, as well as motif-based search. And in this example, we're just searching for structures that contain the keyword hemoglobin. This request is then sent to our API servers, and then in response, the set of matching identifiers is returned. In this case, it's 4-HHB, 3-HHB, and so forth. We have a lot of structures of hemoglobin. On the data API side, you can fetch data about structures. So this includes information like bibliographic data, structural properties, bound ligands, annotations, and more. And in this example, we're just fetching the citation information for this list of structures that was returned earlier. And this request is again sent to our API servers, and then in response, the citation information is returned. So importantly, what this schematic also illustrates is how these two APIs can work together. You can take the output from a search API request where you filter down a set of structures and get a limited set of IDs, and then you can provide that list of IDs as input to your data API to get data about them. So this highlights how all of our APIs can work together and how you can take advantage of them to create your own pipelines. We also offer several additional APIs at rcsb.org. These include our sequence coordinates API, which compiles alignments between sequence databases and protein positional features from multiple resources. In fact, this API is what powers our sequence viewer tabs throughout our website. We also offer a model server API, which provides fine-tuned access to atomic coordinate data in either MMSIF or binary CIF formats. And this API also supports several functionalities within the Molestar 3D viewer on our site. The volume server API provides access to volumetric data for X-ray and EM structures. And our alignment API provides the ability to compute 3D structure alignments between two different chains of structures. For more information on each of these, you can visit this link at the bottom here, which will provide details on each of our APIs that we offer. To help facilitate access to each of these APIs, we recently introduced an all-in-one Python package called RCSB API, which provides a simplified Pythonic interface for our API services, for which the links to the package documentation and GitHub repository are provided here. This was initially developed with the goal of adding support for our search and data API services, as described in our recent publication listed at the bottom here. And the way that we introduced support for them was by creating a dedicated module within the Python package for each API service. So the search API service has its own search API module, which lets you perform all of the activities that you can perform using our search API on our site. And then the data API module is dedicated for the data API service and allows you to perform any of the functionalities that our data API on our site can perform. So since then, we have extended support to additional rcsb.org APIs, including our sequence coordinates API and our model server API. So support for these was added in a similar fashion to the search and data API, in which we created a dedicated module for each API service. Thus, this package is continuing to grow as an all-in-one Python toolkit for working with rcsb.org APIs. And with that, I think I'd like to transition into an introduction into what the sequence coordinate API and model server API actually are. So let's begin with the sequence coordinate API. So the sequence coordinates API offers two main functionalities. First is alignments, in which it lets you get sequence alignments and coverage between a PDB entity or instance, its corresponding uniprot sequence, and or its NCBI genome and protein sequence. So for example, you can get the alignment between a protein chain, a PDB chain, and its corresponding uniprot sequence. And in fact, this screenshot comes from our sequence viewer tab, and I'll be illustrating where you can find that tab later on. But this just provides a nice visualization of what the sequence coordinates API can do. It also lets you get annotations, so you can get positional features and annotations for any given PDB entity or instance, as well as the uniprot sequence or its NCBI genome and protein sequence. These annotations are sourced from PDB data UniProt, Cath, and a large variety of other third-party resources. So for example, you can get annotations at the sequence level of things like binding site, hydropathy, levels of disorder, and so forth. And again, this screenshot comes from our sequence viewer page. So just to provide some example use cases for the sequence coordinates API, in the case of alignment queries, you can use the API to get the alignment between a PDB entity and its UniProt sequence. And what's returned from the API is the begin and end residue numbers of the sequence that you're querying, along with the begin and end residue numbers of the sequence that you're aligning it to. And then you also get the coverage length, so the number of residues that actually span over that alignment. You can also do this by getting the alignment between the PDB entity and its NCBI genome sequence, so you can find where this protein was encoded in its corresponding genome. And you can also get the sequence alignment of all PDB entities within a given UniProt ID. So for a lot of structures on the PDB, a lot of them might share the same UniProt ID, so you can actually just get all PDB entities at once by just querying the UniProt ID. In the case of annotations, types of queries that you might want to perform would be to get all sequence annotations and features for PDB instance 1ABCA. And the type of information that's returned from that type of query is the annotation and feature type. So whether it's a secondary structure annotation, hydropathy, you also get the begin and end residue numbers, and you get any associated values if that's applicable for that particular type. So it'd be like level of hydropathy and things of that nature. You can also filter down the set of features and annotations that you get for a given query. So for example, let's say you're interested in just the binding site features. Well, you can apply that filter to your query and get just those annotations for a given PDB entity or instance. And likewise, you can also get the particular annotation for all PDB instances of a given UniProt sequence. The last thing I wanted to highlight here is that the Sequence Coordinates API does power our sequence viewers on rcsb.org, and this includes our sequence annotations viewer in 1D and 3D, as well as our group sequence viewer in 1D and 3D. And what I mean by that is, if you were to go to any structure on rcsb.org, it typically brings you to this structure summary tab over here. Well, if you navigate over to the sequence tab, you'll be presented with this view, which shows you the alignment between different protein PDB entry chains and its corresponding UniProt sequence, along with the alignment of all the different annotations that have been compiled for this particular protein chain. Furthermore, you could also click on this link here, and you can explore these sequence annotations in 3D. And what that looks like is it brings you to a page like this, where on the left-hand side, we have the same 1D view that we were just looking at, but now it maps every annotation over to the structure on the right-hand side. So in this example, I'm clicking on this particular binding site for this ligand, and it'll zoom in to that particular ligand. So this is an excellent tool for exploring the different annotations and parts of a structure. Furthermore, if you were to click on this link to the UniProt ID over here, it would bring you to a group summary page. So it would look something like this, where you have the UniProt sequence at the top, and then you have all the associated PDB as well as CSM entities associated with that UniProt. And you can also zoom in by using your scroll button to look at specific parts of the sequence. And furthermore, we also offer this in 3D. So you can click on this link here and it'll bring you to a similar view we were just looking at, but this time you can actually overlay multiple entities on top of each other. So all these tools are powered by our Sequence Coordinates API. And it just highlights the value of this API and why you might want to take advantage of it. The Sequence Coordinates API is a GraphQL-based API. Documentation can be found at this link here, which brings you to this page that looks like this. And importantly, this documentation provides information about the actual core API functionalities. It does not provide information on the Python utility. For documentation on that, I'll be sharing that in a moment. But if you want to explore how the API works at a very deep level, I encourage you to please explore this. And one functionality you'll see when you come here is any example that's illustrated on the documentation will have this open an editor link which when you click on it, it'll bring you to our corresponding GraphQL query editor window, which allows you to build your own query, execute them right on a more comfortable user interface. So this lets you explore how the schema is constructed and the different types of data items that you can include and return in your response. All right, with that, I'm now going to switch to the model server API. So the model server API provides fine-tuned access to atomic coordinate data. And what this means is it allows you to extract specific slices or parts of a structure, such as fetching the coordinates of a specific entity or chain within a PDB entry, fetching the coordinates of a particular ligand within a PDB structure. You can also extract the residues surrounding a given ligand, so extracting the binding pocket of a particular ligand. And you can also extract all the ligands within a certain proximity of a given residue. Furthermore, the model server API provides the ability to access structures in binary CIF format, which is a more compressed version of our typical MMCIF format. And an important note I need to make is that this service should not be used for bulk download of coordinate data. Instead, we recommend using rsync or HTTPS instead, which you can find information about at this link here. And the reason I say that is that this API is tailored for accessing specific parts of structures. It's not tailored for performing archive-wide downloads. So for doing that type of thing, please use rsync or HTTPS instead. One direct application of the model server API on our website is through the Molestar 3D viewer, in which the model server API is actually integrated, and it supports several functionalities within the Molestar 3D viewer. The model server API is a REST-based API with multiple endpoints, and if you go to the documentation provided here, it will provide you the list with the list of all the different endpoints and type of queries that you can perform. And importantly, all of these queries are supported in the Python package that I'll be demonstrating shortly. All right, so now coming back to this figure, we can now begin to take a closer look at how these APIs can be accessed and utilized via the RCSB API Python package. So we'll now step into the live demo part of our webinar. And before we jump into that, I just wanted to share some important links. And if you wanted to take a screenshot, now would probably be a time to do it. So at the top, I provide a link to our documentation for the RCSB API Python package. I also provide a link to the GitHub project that hosts this package. And then the webinar notebooks that we're going to be working through are provided at this short link here. This is just a short link. The full URL is provided underneath if you wanted to type that in. One thing I'll point out here is that when we open up the notebooks, you'll notice this little open and collab tag at the top of each of the notebooks. And if you were to click on that, it'll actually open that notebook up in Google Colab, so you can actually run through these notebooks on your own without having to download the notebook and then run it on your own Jupyter instance. But it does require you to be signed into Google, though. All right, so with that, I'm going to navigate out of the slides and go to our notebooks. And this brings us to this RCSB Training Resources repository, which is just a general repository that we use for sharing a lot of the materials and resources that we reference during webinars. So you're obviously free to explore the different webinars that we have hosted in the past, as well as some example use cases that are tailored to specific types of queries of interest. But for now, we're focused on this 2026 Python RCSB API webinar directory. And within this directory, we have 3 different notebooks. We have a Sequence API notebook, which demonstrates usage of the Sequence API module of the RCSB API package. We also have a Models API notebook. And then we also have a notebook that focuses on some more advanced use cases of the Search and Data API. Before I jump into any of these, I just wanted to point out that the link to the documentation is provided here as well. And so if we go to this, Zoom is covering up. All right. Okay, so if we click on that, it brings us to the documentation of the Python package, where on the home page, it shows general information on how to install the package, as well as an overview of the different API services that are supported, in addition to some training materials. So this provides some example notebooks. And importantly, I want to point out there is also the link to our previous webinar, which basically served as part one of today's webinar, which introduces the Python package as well as specific focus on our search and data APIs. So if you haven't viewed that yet, I highly encourage you to take a look at that after today's webinar. On the left-hand side, you'll notice that each section is divided into the corresponding API service that it's describing. So we have a section for the search API, and we provide a quick start page, which just provides you the information on how to quickly install the package as well as how to quickly use it. So a lot of these things you can copy and paste directly into your Python editor and run them. And for each of these, we also provide additional examples. So this provides some more advanced examples for all the different types of searches that you can perform. And I won't go through all this documentation right now. I'll let you explore on your own, but I just want to point out that we have the same thing for our data API, as well as our sequence coordinate API and our model server API. So I encourage you to please review our documentation if you have questions about using the package as well. The other thing I wanted to point out is this link to GitHub here. If we click on this, it'll bring us to the GitHub project that this package is hosted on. We also provide some additional notebooks on here. So if you want to explore our data and search APIs, we encourage you to please check out these notebooks too for some more examples. Another thing that this project can be used for is by reporting. You can use this for reporting any issues that you run into with the actual Python utility. So you can use our issue tracker for doing this. All right, so with that, we can dive into our first notebook, and let's start with the sequence coordinates API notebook. So I'm going to open that up in a new tab. And before I open this up in Google Colab, I want to just stay in GitHub for now because I think it's a more pretty display. So at the top, I just provide some information about the sequence coordinates API. This is all information I just shared in the presentation. But as just a reminder, there are two main functionalities for the sequence coordinates API, and that is alignments and annotations. And so for each of these type of queries, there are a similar set of parameters, but they do differ slightly between certain items. So for the alignments API, the parameters that you're going to be providing are first a query ID, which is the identifier of the query sequence that you want to align. So this can be a PDB entity ID, a Uniprot ID, or an NCBI accession ID. DB from is going to be the data source that this query ID corresponds to. So if you provided a query ID of 2UZI, which is a PDB entity, your DB from is going to be PDB entity. And the full list of possible values that this DB from can take are listed in this table down here. So it can take on PDB entity, PDB instance, Uniprot, NCBI protein, or NCBI genome. And examples of what those identifiers look like are provided on the right-hand side here. So in addition to the DB from, you also provide a DB2 parameter, which will be whatever database that you want to align your query ID sequence to. So in this example, we would be aligning this PDB entity to its Uniprot sequence. And then the last thing is the return data list. And this is the list of data items that you want to return from your query. And this may look confusing at first. It'll become more clear as we work through some examples later. But I'll just tell you now that a good starting set of data items to include would be these three. So this would be query sequence, target alignments, and alignment length. In the case of annotations, we also provide a query ID parameter. And again, this is the identifier of the query sequence that we want to get annotations for. So this can be a PDB entity, instance, Uniprot accession, so forth. Your reference parameter is going to be similar to the DB from in that it's the sequence data set that corresponds to the identifier that you're querying. So if you provide a PDB instance ID, you would request a PDB instance as a reference. And again, this corresponds to this table down here. Your sources parameter will be the data sources from which you want to retrieve annotations. And this can be any one or more of these three options, which would be uniprot, PDB entity, or PDB instance. And then last, you provide a return data list, which again are the annotation fields that you want to include in your response. And again, a standard set to use for your starting purposes would be these three listed here: target ID, source, and features. But again, this will become more clear in a second. All right, so with that explained, let me open this up in Google Colab. And I'm going to install these packages. And GitHub will warn you about this not being authored by Google Colab will warn you about this not being authored by Google, but I guarantee you can trust this. And this will install the RCSB API package along with this other package called Rich, which is just used for pretty printing of our output. I just discovered this package about a year ago, and it has changed how I can debug and display things on my terminal output. So I highly recommend everybody checking that out as well. All right, so that's installed. And I'm now going to scroll down to the first example. And we're going to first work through some sequence coordinates alignment queries. And the first thing that we can try to do is to fetch the sequence alignment between a given PDB entity, 3V851, and its corresponding uniprot sequence. And so the way that we can do that is by importing the alignments class from the sequence module of the API package. And then we're going to instantiate an alignments object using these different parameters. We're going to provide a query ID of 3V851 because that's the PDB entity that we want to align. DB from is going to be PDB entity because that's what this ID represents. It represents a PDB entity. DB2 will be uniprot because that's what we want to align our sequence to. And then we're going to provide that basic set of examples for the return data list that I described earlier. We then execute our query and print the result. When I run this, we see that our result is printed out and it looks like this. And in this, we can see we get the query sequence, which is the sequence corresponding to the query ID that we queried. We also get information about the aligned regions, and we also get the target sequence. So this will be the sequence of the target uniprot that the sequence was aligned to. And one thing you'll notice is that a lot of these return values correspond to what we requested in a return data list. So the query sequence is provided here. So again, that's a sequence of our query ID. Target alignments is shown here, and that includes everything that from the orientation, coverage, target ID, target sequence, and aligned regions. And we also get the alignment length, which is 210, which is the number of residues that span this alignment. In the aligned regions, the query begin corresponds to the residue number of the query ID, and the query end corresponds to the final residue number of the query ID. Likewise, target begin and target end correspond to the begin and end residue number of the target sequence. So one thing you'll notice too is that we requested target alignments, but we got a lot more information underneath that. And this is actually a feature of the package, is that it will autocomplete any sub-nested fields under a top-level field. And so because we requested target alignments, we get everything from orientation, coverage, target sequence, and align fields without having you to type in each of those individually. If we wanted to, we could filter for specifically aligned regions by adding that here. And if we were to rerun this query, we'd see we just get that in response. So you can filter down your response and your results that way if you'd like. But this is actually a feature of the package, is that it spares you the time to type each of those things out. The last thing I want to point out for this example is we printed out this query editor link. And this is done by just running query.getEditorLink. And what this is if we click on this, it'll bring us to the GraphQL query editor window where you can visualize the actual query that we just performed in Python, but now this is in the GraphQL syntax. And you can prettify it by clicking on this button here. And if we were to run it, it would give us the same result that we just got. This The reason I'm showing this to you is because it's a useful tool for exploring and debugging your queries. For example, if you want to explore what other data items are available, you can type control space and this autocomplete little pop-up will show up and you can click on what other items that you want to include. Additionally, you can click on this icon here to view the documentation where you can learn about what each of these items represents. So if you were to click on aligned regions, we would see what each of those subnested fields represent and the definitions of them. So this is just a useful tool for exploring the API, its functionalities, as well as the schema. All right, so now let's move into our second example. Here we're going to do a similar thing, but we're going to get the alignment between the same PDB entity and its corresponding NCBI genome sequence. And so we're going to basically run the same query that we just did above, only we're going to change the DB2 value. So instead of this being uniprot, we're going to specify NCBI genome. And when we run this, we see that we indeed get the alignment between the protein sequence and its genome sequence. So these are corresponding to the base pairs within the genome that align with the sequence, the protein sequence. And for a more visual understanding of what we're retrieving here, you can actually look at the Genome Viewer tab for this entity. And what we see is, again, the alignment between this PDB entity with its corresponding NCBI genome sequence. And if we were to zoom in, you can see the alignment between these sequences. And in this case, it's two different segments. Okay, so the last example for the alignment type queries that we'll perform is getting the sequence alignment for all PDB entities of a given uniprot ID. So because there are multiple PDB entities within the PDB archive that have this, that are of this uniprot accession, we can get all of those at once. And the way that we do that is by, again, importing our alignments class, instantiating the object using a query ID of the uniprot ID. And because that's a uniprot ID, DB from will be uniprot. And we want to align it to the PDB entities. So DB2 will be PDB entity. And then we'll return our favorite list of data items. We run this, we get the response, and you can see that each of the different target IDs corresponds to a different PDB entity. So we have this one, and this one. And again, this corresponds to what is shown here for the group summary page for this uniprot. So you should get each of these. All right, so now let's look at some example annotations type queries. And the first thing we'll do is just try to fetch all the sequence annotations for PDB instance 3v85.a. And the way that we do this is by importing the annotations class from the sequence module. We instantiate an annotations object using a query ID of 3v85.a. The reference value will be PDB instance because that's what this query ID is. It's a PDB instance. And let's say we want to get annotations from all these sources. So uniprot, PDB entity, and PDB instance. And then we're going to return our basic set of data items. When we run this, for now, I'm just printing a summary of the number of different annotation sources that were returned because the actual complete response is too large. But if we click on this editor link, we can see what that general response looks like. And you can see we get information with the mutagenesis site, domains, and so forth. But we see that there's a lot of data returned, and that's why I opted to not print that to the console. However, I do have this little snippet that will provide a summary of that output, and it provides just the list of the different feature types that were found from each data source. So there are 22 annotations from PDB instance, 7 from uniprot, and 4 from PDB entity. So because this response was so large, you might be wondering, how can we filter down that set of results for just the ones that I'm interested in? Well, we can do that by using this filter parameter. And let's say that we want to get just the binding site features for that same PDB instance. So the way that we do that is using the same query we had above, only now we have to import this additional annotation filter input class, which lets us create that object under this filters parameter where we're saying we want only annotations of type binding site. And when we get this, when we run this, we can see we get a much more trimmed down set of results. So this provides a way to filter down your results and get exactly what you need. Last, you can also get the binding site features for all PDB instances of a given UniProt ID. And so here, instead of providing that PDB instance as the query ID, we're providing the UniProt ID. And because of that, the reference is now UniProt. And because the binding site annotations were coming from PDB instance above, we can just limit our sources to just be PDB instance. And then I'm now applying a little bit more filtering here for the return data items, just because a lot of these are null or redundant, so we don't need all of them. And then we're going to apply this filter of binding site. And so when we run this, we get a total of 7 annotations, but I'm not printing them here for sake of how large the response will be. The last thing I have here on this notebook is just explaining how you can print the query editor link, but I've already demonstrated that, so I will skip that for now. And for any other documentation and for more examples, please visit our Read the Docs page here. Okay, so with that, I'm going to close out. And we can now switch over to our Models API notebook. And so I'm going to click on that. And so similar to our sequence coordinates API notebook, I provide some just general information about how the API works, that the model server can be used to fetch specific parts of a structure, like getting specific entities or ligands from a structure. And I also provide a list of the different methods and parameters that would be accepted. So this model query class has multiple methods, and each of these corresponds to the possible endpoints in the actual API service. So you can get a ligand, get specific atoms, get residue interactions, and so forth. And for most of these, the query parameters will be quite similar, but obviously they will differ a little between the specific method that you're using. For pretty much all of them, these parameters will hold true. So you'll provide an entry ID, so whatever entry ID that you're interested in. You can also specify the encoding, so whether you want to return the data as MMSIF or binary CIF format. By default, it's in CIF, MMSIF format. You can specify that you want to download the structure. You can specify a file name, a file directory, whether you want to compress the file, and this copy all categories parameter, which controls whether you want to return all other metadata categories from the source entry file. Now, depending on the specific method that you're using, these additional parameters will come into play. So this just lets you provide more fine-tuned control about what type of data you want to return from a particular structure. So whether you want a specific entity, a specific chain ID, or a specific ligand, these would be the parameters that you would use. So with that said, let me open this up in Collab. And I'm going to first start by installing the package. And while that's running, I can scroll down to our first example. And so for our first example, let's just pretend we're interested in fetching the coordinates of the heme ligand from PDB entry 4HHB. And we're going to do this using the getLigand method. So the way that we can achieve this is by first importing the model query class from the model module from the API package. We then instantiate a model query object, and then we run the getLigand method using the specific set of parameters that we need for this query of interest. So we're going to specify we want query entry ID of 4HHB. Our chemical component ID will be heme, and we want to download this and save it to file name 4HHB heme ligand.cif, and we're going to save it to this directory. When we run this, Google Colab will print out the location of that file. And what's kind of nice about Google Colab is it actually does save that file. If you click on this icon here, it'll show you the list of files that are associated with this environment right now. And so we could download this and look at the coordinates of specifically the heme ligand. Now, importantly, this get ligand method specifically grabs the first occurrence of that ligand from a PDB entry. If you want to get the coordinates of all heme instances from a given PDB entry, you want to use the get atoms method. And so that's what we're going to do for our second example. So here again, it's going to be basically the exact same thing we had above, only now we're using the get atoms method, and we're going to give it a different file name. We're going to say this is 4-HHB heme atoms.civ. Also, I'll mention if you don't provide a file name, the package will try to construct one for you automatically based on the different parameters that you provide. But it's just good practice to explicitly provide your own file name. So I'm going to run this, and we get this as output. If we refresh our file list here, we see for sure we get our resulting file. Next, let's say that we're interested in the binding pocket of heme instance E within that PDB entry. So we can use the get residue interaction for this. And what it will do is grab all surrounding residues within 5 angstroms of heme instance E within that entry. So the way that we do this is, again, importing our model query class, instantiating the object, and then we're going to run get residue interaction using these parameter arguments. So our entry ID will be 4-HHB, our component ID will be heme, our chain ID will be E. You can specify the radius, so we're just going to use 5.0 for 5 angstroms, and we're going to download it to a different file name. And when we run this, we get our result here. So again, we can refresh, and I wish I could display these files, but I can't do that directly on here. Last, we'll look at fetching the coordinates of all ligands within 5 angstroms of a particular residue. So let's say we're interested in all the ligands around alanine 284 of PDB entry 1TQN. And we do this using the get surrounding ligands. So we're going to run this method and provide our entry ID is 1TQN, our component ID is alanine, sequence ID is 284, so that's a sequence number, our radius, and then we want to download it. And note that I'm not providing the file name here, and this is just to illustrate how the package will automatically try to construct it for you. So it'll just take on a generic name that looks like this. And if we refresh, we see that it's saved here. Okay, so that concludes all the examples for the model server API. For more documentation on them, I encourage you to please view our read the docs page, as well as the model server API specification. So the last notebook I have prepared for you is this notebook that covers some advanced use cases of the search and data API services and modules. So I'm going to open that one up. And specifically, the advanced use cases I'm going to demonstrate are first performing a structure similarity search using our new AI-powered 3D search service at rcsb.org. I'll also demonstrate how you can group your search results based on a certain level of sequence similarity. And then last, I'll show how you can fine-tune the RCSB API package using the different configuration options to optimize your performance. So I'm going to open this up in Google Colab. And I'm going to install the package. And so the first thing that we're going to work on is performing a structure similarity search using our new AI-powered 3D search service. So we've recently introduced a new AI-powered 3D search service, which can perform archive-wide similarity searches at a scalable and efficient speeds. And along with this release, introduced several new parameters for our structure similarity query class that was already provided in our package. So specifically, the new parameters that are added are similarity type, number of candidates, and PTM score cutoff. And for more details about all the available parameters, please check out the documentation. So to provide an example of how to perform a 3D similarity search for PDB ID 4-HHB, you would construct it as follows. So you'd first import the struct similarity query class and instantiate that object. And we are going to perform our search using entry ID 4-HHB. So our structure search type is entry ID because that's what we're searching. We're also going to specifically search for assembly ID 1. And that means our target search space would be assembly. And we're going to use a similarity type of local. And this parameter can take on either local or global, where local favors matches to specific regions of a structure, and global applies a length normalization to favor global similarity. We can also specify our number of candidates as 10,000, and what this does is it controls the maximum number of similar matches that can be returned. And then we also specify a PTM score cutoff, which is basically the minimum predicted template modeling score threshold above which hits will be returned. And so this is on a range of 0 to 1, and we'll provide 0.8. When we run this, we're going to print the number of results we get, as well as just the list of the first 10 matching IDs. And we see that we get 1,700 results, along with the first set of matching identifiers. And it makes sense that the top scoring similar assembly is for HHB1 because that was the assembly that we actually queried. So you can't get closer than that. And then everything below that are more similar, other similar 3D matches. Another important feature that I'll point out is that you can actually perform these searches using your own structure models. So if you're running AlphaFold on your own or any other structure prediction software, you can actually perform searches across the PDB archive using that structure as input. So you can find whether structures exist in the PDB archive that are similar to your own generated structures. And the way you can do that is by providing a path to the file and then specifying that your structure type is file upload. I don't have a file saved on Google Colab right here, so instead I'm going to use the URL-based form. And so here I'm going to provide the file URL to 4HHB.sif, and that means our structure search type will be file URL, and every other parameter will be the same as what we did above. So when I run this, we should get the same number of results that we got here because we're performing the same query, just using an uploaded structure instead. So, and sure enough, that's what we get. We get 1,701 search results, which matches from before. Okay, so the next advanced use case I want to demonstrate is how you can group your search results by sequence identity. So when you perform a search on rcsb.org, especially for something like an enzyme where this enzyme might exist multiple times, you might want to find a way to consolidate your results based on a certain level of sequence identity. And you can do that by grouping them either by uniprot or by sequence identity. And so for this example, we're going to use the search API to group all protein entities in the PDB from Arabidopsis thaliana, and we're going to group them together by 90%. And then we're going to return just the list of the representatives for each of those groups. And then we're also going to create a little bit of a pipeline. We're going to then use those representative structures as input to the data API to retrieve the associated one-letter sequence code and cluster IDs of those representatives. So for the first part, for the search API part, the way that we would do that is first by importing our various attributes, and we also import this group by class. And then we're going to construct our query by creating these two subqueries, first for filtering for structures that are proteins, and then we're going to filter for structures that are of the organism Arabidopsis thaliana. We then group those two subqueries together using the AND operator. And then what I'm going to do here is first print the ungrouped search results, just so we have a baseline that we can compare the grouped results to. And then in order to actually perform the grouping, we execute our query by providing a group by parameter with the value of this group by object, in which we're specifying we want the aggregation method to be sequence identity, and we want the similarity cutoff to be 90%. We then specify that we want a return type to be representatives, and we're going to return polymer entities. And so when we run this, we should get the list of ungrouped and grouped results, as well as the first 5 representatives. And so what we see here is for the ungrouped, we get 4,467 entities, and in the grouped results, we get 1,428. So you can see the significance in consolidating results using this group by method. And the first 5 representatives here are just printed in this list. And one thing I'll point out is that these representatives are just one member of a group with no particular ranking applied. If you wish to apply a particular ranking, so like if you want to pick the best resolution structure of each group, you can also do that, and you do that using the ranking criteria type and specifying which attribute to use for your ranking and sorting. And I provide an example of how you would do that here. So this will bring you to the read the docs page, which will demonstrate how to perform that level of ranking. Please note, though, that if you do that, this might impact the performance of your query, especially depending on if your result set is very large, in which case it might take a long time to run. So that's just something to keep in mind. So now for step 2, the data API part of the example, where we want to get the sequence, the one-letter sequence code and the cluster ID for those groups. What we can do is by importing our data query class from our data API module, instantiating a query object, and we provide as input the search results that we just got above. And these are of polymer entities, so input type will be polymer entities. And then we're going to return the data items of cluster membership ID, identity, as well as one-letter sequence code. And then we can execute and print our results. And here I'll just print the first example of the result. So the first matching ID was 1IRZ1, and the corresponding group ID for the identity of 90% will be found here. And you can use this ID for other downstream work if you wanted to look at other members of that group. And then we also get our one-letter sequence code, which is shown here. Okay, so the last advanced thing I want to demonstrate is how you can fine-tune the RCSB API package for optimizing your performance. And there are a variety of configuration options that exist for the RCSB package that you can use to control its performance, such as the number of requests to perform per second, your API timeout, as well as input ID limits for certain modules. And the full list of these can be found here. And so again, you see things like timeout, max retries, and these are all things that you can configure. And one thing that we'll focus on for this example will be the data API max concurrent requests. So this is the maximum number of data API requests to run concurrently. And so to demonstrate this, the way that you can set any configuration is just by importing this config object and then overriding the default value with what you want it to be. So it's as simple as that. And for this example, we'll just run the same query we had above, but we're going to do this on the ungrouped search results. So this should be about 4,500 entities. And we're just going to measure how long this takes. And I'm just resetting this here in case you run this out of order so that for consistency. So you don't need to rerun this every time, but I am just doing that in this cell. So when I run this, we see that that took about 1 second to run. And if we lower now the concurrency down to 2 and we run the same query, it takes about 2.2 seconds. So that pretty much tracks, and you would see that you get somewhat faster performance if you increase the concurrency. Now that said, I have to emphasize, please do this with extreme care and caution. If you increase these settings too much, it can actually be detrimental to your queries because it may consume, you may end up generate too large of a response, or it may too aggressively hit our servers, in which our servers would respond with a 429 code and inform you that you're exceeding the threshold of requests per second on our site. So please adjust these with caution and care, and especially with regard to friendliness for working with our API servers. Okay, so with that, I think that concludes all the notebooks, and I'm going to come back now to our presentation. And so what I wanted to show here are just some of the resources and links that I shared earlier. Again, if you wanted to take a screenshot, now is an opportune time to do that. I provide a link to our Python package documentation, the GitHub project, the notebooks that we just worked through, as well as where this webinar recording will be posted. So it'll be posted on pdb101.org under our training events. Additionally, the previous webinar that introduced this Python package can be found at this specific link here. If you have questions after today, and these questions are specifically related to the Python package, like if you're running into issues with importing different modules or running different snippets of code, please report them on GitHub using our issue tracker. If you have questions, though, that are more related to our APIs, our schemas, and the data, like what type of data you can get from our APIs, how our APIs work, or if you're running into 500 errors with the Python package, please use our Contact Us button, which can be found here on our site, as well as emailing us at info@rcsb.org. With that, I'd like to acknowledge the entire rcsb.org team for all their contributions to our resource and all the different tools that are available. In particular, I want to highlight Ivana Churang and Krish Parmar, who were the key developers behind the sequence coordinates API and model server API support for the Python package. And of course, I'd like to thank our funding from the U.S. National Science Foundation, the National Institutes of Health, as well as the Department of Energy. And I'd like to thank you all for your attention.